Okay, so let me now formally start the class. I have started recording. I will close chapter 1 and I will resume from chapter 2. All right. So not yesterday, day before yesterday, Wednesday, during the class, I said that there are some problems with the notation here in the valuation equation. But then we checked, and actually Dev Surjo told me this morning that he has also checked. The notation is actually fine. What is happening here is the backward induction argument that when I'm solving the valuation problem at time tm minus 1, which is given by this expression here, I am going to use the solution starting from the next period onward. So for the tm minus 1 expression, one of the inputs here is the tm time expression, which is the period just after tm minus 1. And that's how this whole dynamic optimization problem will be solved. This is the general principle. So this is not only true for a financial option pricing situation. This is true for any dynamic problem solving situation. So what we are going to do is we are always going to start from the last period, because there is no tomorrow. Last period problem is typically the easiest one to solve. There is no continuation value. Once we get that value, then that is used as an input in the last but one period, and successively till we reach time 0. So at each time point, all the solution numbers from the next period are going to be used as inputs. So it's a recursive kind of solution. And that's how it usually works. Numerically, it can be quite complicated. In particular, you can see for the Bermudan option that once I start doing this recursion, I have to do a lot of quite complicated calculations. So I have to find out expressions for the continuation and the exercise value for each period. They are again going to involve all the later period values. So I have to do integration here, of course, numerically, which is like doing this summation and truncating it at some point capital N minus 1. That will involve these coefficients here again for the continuity and exercise like this, so that finally we will be able to write a recursive system of equation for the value at time 0. And how is this going to start? This is going to start at the last period. So at the last period, T capital M, we are only going to look at the exercise values. Then I am going to use these things as my input into the problem for T capital M minus 1 and so on. Doing all these things successively till time 0, this 2.68 is the final expression. Where when I am evaluating the time 0 values, I am using the first period, T1 periods, V function. So I start with V at T capital M, calculate backwards, get to VKT1, and this is the final expression that I will get. So it's a lot of calculation, but of course, in a computer program, it will be done recursively. So you just need to write a loop. So the loop will run itself out till time 0. So again, I hope that you have actually looked at this. Some of you did, so that's good. Are there any other confusions here? Because Wednesday, I myself was confused, so I'm sorry for that. But it's good that things have been clarified. Is it clear to all of you?
Yes, sir.
So the agenda of the topic was whether we can also use the same cosine method for path dependent option. And of course, when I say path dependent, it has to be discretely monitored, because if it's a continuous time problem, then you cannot use it. You cannot use the cosine method to do anything with that. But now that we are restricting ourselves to discretely monitored path dependent options, so Oosterley and Fang used the backward induction algorithm to compute the explicit valuation expressions for the path dependent Bermudan option. So now let me also talk a little bit about a second application, which is discretely monitored barrier options. So if you recall, barrier options are options which becomes worthless if the underlying price hits a barrier. So I have this lifetime from 0 to capital T, and I look at the evolution of the stock price ST. The option could be simply a call option, but I have the additional clause that if at any point of time between 0 and T, my stock price crosses a particular pre-specified value, let's say capital U, if it goes above capital U, then the option becomes worthless. It could also be some number below. It could also be a put option, or we can have a reverse situation where the option will become active only when it crosses a barrier. So all of these different combinations we discussed last term: up and out, down and out, up and in, down and in. So, and we showed that basically the analysis is similar. So if you can work with one of them, then you can deduce the others by similar logic. So again, here also, we are going to talk about an up and out option, which means my option will become worthless if it goes above a pre-specified. So this is how the payoff is defined. So VXT is, this is a call option. So it's a maximum of XT minus K0. So if alpha is 1, then it's a call. If it is -1, then it's a put. Provided I never cross a barrier capital H. So if I cross the barrier, then I will get a fixed amount capital R. In our classical examples last time, this capital R was equal to 0. Here also you can safely take it as 0, but sometimes there is some rebate clause in a barrier option, which says that if the option becomes otherwise worthless, you still get some small amount as a consolation. So this is the consolation price. So you have an R, which is called the rebate, and H is my barrier. Now, in the classical definition, again, the barrier option was monitored continuously. So it says between 0 and T, if at any point of time it crosses the barrier, it becomes worthless. Again, numerically, any point of time cannot be checked, and we cannot use our dynamic optimization algorithm. So we restrict ourselves to a discretely monitored barrier option. So we do not check the price at, we do not check the price continuously. Rather, we just check the price at, again, some discrete set of time points. We can use the same notation like this, T1, T2 up to T capital N. So I pre-specify on which time points I will check my stock price, and then the discretely monitored barrier option says that the option will be worthless if the stock price at any of those time points goes above H. Okay, is the definition clear? It is the barrier option, up and out, but instead of monitoring it, observing it continuously, we observe it at discrete points of time which are pre-specified. So at pre-specified dates, pre-specified time points, I'm going to check barrier condition. So that is more or less easy, I suppose. So R is the rebate and X is the level of the price. The formula for this coefficients VKTM. So remember, we are using the same notation. So we are again going to use this kind of expressions, and I need to have these coefficients VKTM evaluated. So again, those expressions can be done using two parts. Earlier, the two parts were whether I exercise or I continue. Now the two parts are whether the stock price hits the barrier, so the contract terminates, or it stays below. So my VKTM has these two components. The CK is the continuation component, assuming that the price did not hit the barrier. This is the continuation component, and this is the rebate component. The rebate component corresponds to the situation where I have actually hit the barrier, so the contract gets terminated. And this is the expression for that rebate part. Of course, there is a time discounting involved because I am going to evaluate everything at time 0. So again, for pricing this option, we will start from the last monitoring date, which is the terminal date, T capital M, and VK T capital M will be given by, this is my final exercise value or the rebate, and for a put, again, this is the final exercise value or the rebate. If in case my capital H is so small that log H is less than 0, then this is the expression. If it is more than 0, then it is just a modified expression like this here. But in principle, it is the same. So what I will have is whether I am going to be able to exercise my option at time Tm, or I just get the rebate. And then the same logic follows. I have this expression to connect my valuation with the subsequent continuation value. See, this is my continuation value, and these continuation values are going to be successively computed recursively starting from the last time. Again, it will be an algorithm with a loop, but the eventual expression can be numerically obtained. So what we have done is we have talked about possible situations where the cosine method can be used to price path dependent options. It has to be a case where we only observe the stock price at discrete points of time. Otherwise, we won't be able to use the dynamic programming that we are using here. The two examples that are worked out are one for the Bermudan option, where I have some pre-specified possible exercise dates, or I have a discretely monitored barrier option where my barrier condition is checked at a set of pre-specified dates, not continuously. And I use similar logic of dynamic programming and get the solutions. So is this okay so far? I mean, not the expressions. The expressions are complicated, that I admit. But is the logic clear? What we are trying to do? Sorry? Log of capital H. So this is generically the notation. The small letters are log of capital letters. So Wednesday we talked a lot about dynamic programming and backward induction. So I thought that I will just give you a small informal introduction to that algorithm. This is not part of the course, so I'm not going to set
Sir, I
problem.
think sir, this age should be standardized. Like this knowledge should be something like log of capital H by X naught,
Huh, of course,
initial price.
of course, it is always uh,
It has to be
normalized by
standardized.
time zero value. Oh,
Yes.
right, of course. But I think that is the convention we have been using throughout. You see, if you look at this small x here or this y here, we are always using that convention. So because it is just continuing on the first example, so these notation are not explained again. That's all right. So it is normalized, certainly. So because I do have a strike price here, uh, where is the contract specified? Yes. So I do have a strike price here, capital K, and everything is normalized by K. Then log. Okay. So before I go into this next part of this chapter, let me take a quick detour and tell you a little bit about dynamic programming. This is something uh, that is extremely useful in most of the engineering sciences theory, at least theoretical engineering sciences, a lot in physics, economics, and of course in finance. Because in all of these subject areas, we often have problems of optimization over a length interval of time. So you have to take optimal decisions on the same objective multiple times because the objective is either minimizing cost or maximizing output over a period of time, not a single period. It's not a one-shot problem because the one-shot problems are easy. We just do uh, Lagrange problems. But if I have to do it over a period of time, then this is the tool that is used by all of these people. So this is the dynamic programming algorithm. And this is the book by Bartsekas. Bartsekas has a very nice textbook on dynamic programming. So I'm not going to talk about the whole thing. So I'm just going to tell you how it works. So let me first show you the example. What is the example here? The basic problem. No. Where is the example? Oh. This is the example. So it's an inventory control example. So what is happening here is that I am using a certain item, and the quantity of the item that is currently available with me, say at time t currently available with me is xt. Somebody is going to buy it from me. So somebody is going to place an order. And I don't know exactly how much order will be placed at each time point t. So I have some stock available, but then the order that comes to me at the beginning of the period, this ut, may not be equal to xt, of course. So the demand during the time period is wt, and this is where I assume that there is some randomness. And because it is random, I cannot anticipate it completely, but I have to keep a backlog and then make it up in the next period. So what will happen is that some additional, some demand is coming. If I can meet it, fine, but if I cannot meet, then there is some excess demand that remains on my ledger that is backlogged and filled as soon as additional inventory becomes available. So what will happen to my stock? So I already had something from before. I will order something in addition. This is in my control, but people are going to take things from me, and that quantity is not in my control, and that I consider as a random quantity. So in any period, the action that is going to happen is I start with some initial, I get something additionally, but I have to give out some WT. So when I go to the next period, this is what I am carrying with me. And this can be negative. If this WT is very large, then it is possible that this will be negative. Now, what am I trying to manage? What is my overall cost and profit function? I have two components here. There is a cost or a penalty for either excess positive stock, because I have to maintain an inventory, and maintaining an inventory has some cost, or there is a negative stock, and then I have to pay a penalty for the delay, because the order has been placed today and I am not able to meet it completely. I have to pay an additional penalty for the delayed delivery. Tomorrow I will be able to deliver, but I have to pay a penalty. So either it could be holding cost or it could be a penalty. And of course, I have a purchasing cost, per unit purchasing cost for the amount that I get in. Overall, this is the cost that I want to minimize. How is this calculated? For each time period, I have this inventory holding or late penalty cost, RXT. What is going on? I have this inventory cost or late penalty, and I have the purchasing cost, and that is aggregated over time. And in the end, at time capital T, when there is no more business to be done, whatever excess stock I have, that will also have a terminal cost capital, because whatever I have in my hand, I cannot use anymore. And of course, I cannot order negative quantities, so my U quantities are non-negative. So this is the problem. This is my problem. So I have these things. X is what I have, U is what I do, and W is what I receive, which is random. So these are like the states of nature. This is my control. This is called my control. And this is the initial state. So from the initial state, I do some controlling and I face some state of nature. I go to the next state. This is the transition. And my objective would be to minimize this expected value. I have to do expectation because I have W's random. Okay, so quickly going to the algorithm. I won't go through the whole thing here. So this is the dynamic programming algorithm for the example that we just discussed. What do? We go straight to the last period, capital T minus 1, last but one period. Because at time T, there is nothing to be done. We go straight to capital T minus 1, where I have stock X capital T minus 1. So clearly, I must order some amount U capital T minus 1. No matter what happened in the past. And how should I order U capital T minus 1? I will look at my cost from capital T minus 1 point onward. And I want to minimize that cost. Now, what is that cost? If I order U capital T minus 1, this is the ordering cost. This I know exactly, no problem. Per unit cost is small c. But there is one random part, because after I have ordered U capital T minus 1, WT minus 1 order will come. So I will be left with this final inventory, x capital T minus 1 plus u capital T minus 1 minus w capital T minus 1. And this will be remaining with me because tomorrow is the last day. So I have to calculate an expectation of this R over possible W T minus 1. So this is my objective function for period capital T minus 1. I know this exactly. So there is no summation because there is no tomorrow. And the solution to this, we denote by this symbol capital J. So what is capital J? Capital J is some terminal cost and the minimizer of this thing. Minimizer for all possible non-negative choices of U. I have to solve this. It can be done if I know about the probability distribution for W. So Jt minus 1 will come out as a function of xt minus 1, the stock that I began with. Once I do that, the optimal U that I get from this minimization exercise, let me call that mu star T minus 1. So this is my optimal choice for the T minus 1 period. I know this now. Now I go to the previous period, capital T minus 2. Now what do I need to do? Using similar logic, now I have to look at the expected cost of period T minus 2 plus whatever the expected cost of period T minus 1 will be, given that tomorrow at T minus 1, I will be using that optimal policy mu star T minus 1. So at T minus 2, I know that tomorrow I will play the optimal thing. Knowing that, what should I do today at T minus 2? Similar logic will tell me that this is the expression that I am going to face with. I already know tomorrow's minimizer solution. And this equation will connect xt minus 2 and xt minus 1. So what will happen is, today's minimizer Jt minus 2 can be written like this, where instead of xt minus 1, I have used this equation and written it out. Again, the same minimization exercise over ut minus 2, which will give me mu star T minus 2. And you know the rest of the story. We will continue this way till we reach the beginning. So now we can, it's like an induction step. So I can do this for any intermediate period. And finally, if I continue this way, I will reach J naught X naught, which is the optimal solution for the entire period. And in the process, remember, in the process, I have also calculated the optimal order for each time period. So I solve for mu star T minus 1, then I will solve for mu star T minus 2, etc., etc. So in the end, I will have a vector mu star 0 to mu star T minus 1, which are the optimal decisions that I should be taking every day of this whole problem. And the principle of optimality simply says, it's a very intuitive statement. The principle of optimality says that let pi star be this vector of this optimal policies, mu star to mu T minus 1. Assume that when I'm using pi star, a state xi occurs at some time I with positive probability. Now, suppose I think of the problem as if I am starting from time I with xi. So forget about the beginning. I start from time I, and I consider only the cost pertaining to the remaining periods. Then I don't need to recalculate my pi star. The truncated policy starting from mu I is again optimal for this sub problem starting from I. Okay. So is this clear how the dynamic programming approach works? Because I just thought that it might be good to show you the general idea, at least through an example, informal.
Yes, sir.
So of course, this is a different course in itself, but this is used so much in finance that at least you should have a taste of what dynamic programming is like. Okay, all right. So I think we have done enough dynamic programming. Now let me come back to finance and let us look at the numerical results. So what are these numerical results? So we are basically trying to see how good the cosine method is. So we claimed that cosine method is the fastest of these characteristic function methods. So numerically, we want to see how good it is for some of the standard models. So first of all, if I compare cosine with Monte Carlo, which is the most general method, but also the most expensive method, because you do not make any assumption and completely rely on simulation techniques. So for this example, two models are considered. One is the Black-Scholes, where I have analytical solutions and things are pretty much well defined. And the other one is the variance gamma model. For Black-Scholes, these are the parameters. These are more or less standard. Initial stock price 100, strike is 100. I have 1 year maturity period. I'm going to monitor 12 times. So basically once each month. The barrier is chosen as 120. There is no rebate. So this is the classical barrier option example. I have a 5% risk free rate and the volatility. For the variance gamma model, in addition, I have taken sigma equal to 0.12 nu and theta. So we are comparing the discretely monitored barrier option pricing using cosine versus using Monte Carlo. So this is the result. So if my model is Black-Scholes and I am using 2 to the power 6 many observations in cosine rather than 10 to the power 6 in Markov chain Monte Carlo, the call prices I obtain and the put prices I obtain are like this, which are both pretty much close to the theoretically correct price, because in this case I know the theoretically correct price, but the time taken is much less for the cosine method, obviously, because I am using fewer sample points, much less than the Monte Carlo method. If I go to the variance gamma method, now again I use the same kind of comparisons and I get comparable results with these comparisons, but again the time taken, it is very much in favor of the cosine method. And remember that in this case, I do not have analytically closed form expressions for option prices always. So we have to rely on Monte Carlo to get close to the theoretically correct value, but that is going to be very expensive. So this example highlights that with much less time, which means with much less cost, I can arrive at a fairly good solution, correct up to the second place of decimal here, fairly good solution using the cosine method. It's much cheaper. So that's how it stacks up against Monte Carlo. Monte Carlo we haven't discussed yet, we will do later on, but Monte Carlo is typically the general most powerful method. Okay. So we'll close this chapter with some overall numerical results. Some of the standard methods are compared here side by side. So what are the methods? I have the Black-Scholes analytical pricing for the classical geometric Brownian motion case. I am using the cosine method in the second column, fractional FFT, and this is the saddle point method, which I am omitting, which I am not teaching. So you can ignore the last column. So these 4 columns are relevant for this example. And Of course, the Black-Scholes is analytically computed, so it is exactly correct. So this is our benchmark, and we are looking at these three other methods for different strike prices. So again, it's a similar situation. I have initial stock price 100, and these are the other parameters. So for different strike prices, these are the values that I get, and we already know that for near at the money options, this cosine and Fourier transform methods are very good. So when I'm operating at say 90 or 80 or 110, 120, which is close to the stock price, initial stock price, the precision of these methods are quite good. When you move away from the strike, away from the stock price, when my strike is very low, say 10 or 20, then of course, cosine method does not work well. We have already said that in the beginning that cosine methods do not work well for out of the money options. Whereas the FFT type methods, they do better. Okay. When I come to more general models, so we also look at the Heston model with these parameters here. I have these additional parameters, kappa, sigma, theta, etc. So for Heston, I do not have a theoretically computed expression. So we rely on the Monte Carlo method to give us the theoretically correct result, the within quotes theoretically correct results. So our comparison will be all these other methods with the Monte Carlo result. So instead of the Black-Scholes here, which we had, we now have the MC column here. And again, similar conclusions you can see that when I am near the stock price, these methods work comparably well. When I go farther away, then the cosine method starts moving away from the correct solution. But at least for Heston model, the FFT methods also starts moving away from the correct solution. So they are equally bad as the cosine. And finally, for the variance gamma model, European call, I have a similar example shown here with similar kind of results. For at the money options, I have good results. And as I keep moving away, the prices become more error prone in case of the cosine method. In fact, cosine method now starts doing worse than FFT or fractional FFT, because these are still pretty much close to the analytical price, but cosine shows bigger errors. CGMY, the last model, the most complicated model, lot of parameters. Again, similar kind of results, but of course now the precision is not as good as before. So when the models become more and more complicated, my comparisons become also difficult to do. Okay, so that actually brings us to the end of chapter 2. Are there any questions that you want to ask me immediately? Of course, I have.
Sir,
yes.
Sir, breakটা এখন দিলে আর কি লাস্টের পার্টটা দেখে নেব এক্ষুনি।
Sure. আমরা এখনই ব্রেকটা দেব, obviously. Before I go for the break, all I want to say is, now that we have finished chapter 2, now that I have finished chapter 2, these problems become live. So from chapter 2, the problems that I want you to do from HITSA are problems number 1 to number 7. So now this gets added to your portfolio, and I will take a break. We will resume in around 15 minutes from now. Okay, so let me resume the recording and share my screen, because now I want to move on to not to ESPN but to chapter 3. Chapter 3 is the finite difference method. So this is something that you all know. You have all learned the forward difference, backward difference approximations in some course somewhere, right? This is familiar to all of you, isn't it? The finite difference technique, at least
Yes,
in
sir.
some form.
Yes, sir.
Yes.
Yes, we learned it in numerical analysis.
You learned it, I think, in the first year itself. I think in our BStat course, in the first year there was a course where we learned all these things. And similarly, in the BSc Statistics Honors, there must be something, isn't it? Can someone from the...
Yes, sir.
Yeah, right. Thanks, Himantri. All right. So we know what is the finite difference technique, and we also know how it is done. Now we will use that technique for our purpose, which is obviously pricing different financial contracts, derivative contracts. So in particular, we are going to look at this finite difference technique and its use to solve PDEs and PIDs. PDE for the purely continuous type stock price processes with density, and PID is when there are discrete jumps, discontinuities, particularly discrete jumps. So we have talked about Levy processes, so we know where these jump models come in. And when you do have jump models, we will see that we will not have nice PDEs. Instead, we will actually have integral differential equations. But anyway, the finite difference techniques will be the same toolbox, and there will be 4 methods in particular, 4 methods that we will be talking about: explicit, implicit, Crank-Nicolson, and multi-step. Why are we learning so many? We will see that it achieves different levels of precision, and also there are computational complexity issues. That's why for different situations, different techniques might be helpful. So we start with the simpler ones, explicit and implicit schemes, and then the other 2 are essentially generalization of these 2, where we achieve certain goals, like in terms of higher precision or better computational time. We will discuss them one by one. So the starting point is, of course, the Taylor series. The Taylor series expansion. So if I assume that f is a superbly smooth C infinity type function, so all derivatives are continuous, and I do a Taylor series expansion of fx around a, some point a, which is given by this. So this we all know. There is nothing to talk about here. Our starting point for the finite difference technique will be how many terms in this expansion are we going to consider. That's where the story begins. So let us look at the forward and backward difference approximation of the first derivative. So this talks about derivatives of all orders. So in particular, I want to understand about the first derivative, and I want to make an approximation for that. So if I am talking about only the first derivative, it is enough to assume that f is a C2 function, because right now I don't need more. And we are interested in approximating f bracket 1 using this notation here, f bracket n is the nth derivative, so f bracket 1 is the first derivative at x. I use a truncated Taylor expansion in two different ways. One is I start from the forward one, which is fx plus h is approximated by fx plus h f1x plus this correction term, which is of the order h squared by 2 factorial. So if I ignore this term, then it will become an approximation. And the backward expansion, which is fx minus h, which is same in spirit, only I insert minus h in place of plus h. So these two are my forward and backward first order expansions. So I take only the first order term and collect everything else in this term, where this xi1 and xi2 are some point between x and x plus h, or x and x minus h, as the case may be. So from the forward expansion, if I solve for f1x, I will get this forward ratio, fx plus h minus fx by h, minus the correction term. And now I make the approximation assumption that this is my approximate expression and the error of approximation is comparable to h. Because in Taylor series and numerical analysis, we have learned that whatever we ignored, if we stop at any point, then all the remaining terms that we have ignored will be of the order of the last term that we considered. So here the last term that we considered was the first order term, h order term. So whatever we ignore will be of the order of h. This is known, right?
Yes, sir.
This is something that we have learned in the first year or somewhere in our undergraduate. So 3.3 will give me one approximation for the first derivative, which is 3.5, and 3.4, the backward expression, will give me another approximation for the first derivative, which is 3.6. Same principle, only I am using either the forward difference or the backward difference. So obviously these two equations, 3.5 and 3.6, are called forward difference and backward difference approximations of the first derivative, and both have the order, both have error of order h. So we call them approximations of first order. Approximations of the first order because their error is of the order h. I can do better. I know we have the first order, backward and forward, but we can do better. We can combine these two things and get a better error, smaller error. But the cost is I have to assume that the function is smoother. So now suppose my function is C3 and I want to achieve a second order approximation of F1. Error will be h square. So again, I use Taylor series, but now I expand up to the second term. So I collect the third term onwards. So in the forward expansion, I have taken the second derivative term explicitly, collect the remaining things. Similarly in the backward difference. And if I now subtract 3.8 from 3.7, what I will get is this equation where if I subtract, then this first term and the third term will cancel each other out. So I will be left with twice the middle term, the second term, and the two errors. And then again, same logic. I know that whatever I have ignored will be of this order because I am having h cube terms here. So my error can be at most h square. So if I now use 310 for the approximation of the first derivative, then it is called the central difference approximation. The central difference approximation is just this difference divided by 2 to h, and of course the error will be less. Order, it is now of order h square because I am using the second derivative term also. So it's a better approximation. Continuing the same logic, I can use the central difference approximation again for the second derivative. So certainly I will need more smoothness. So if f is in C4 and I want to estimate f2x, I will now use the expansion up to the third term. I have to take the third derivative term also in both of these equations. So my error is starting from the fourth h power 4. I add them up. If I add them up, I will cancel the odd terms, the second and the fourth term here, they will cancel out. So what I will have is this expression 314 and then simple arithmetic solving for f2. This is my approximation for the second derivative, central difference approximation, and my error will be of order h cube. So this will be h cube. This is wrong. This will be h cube because I have used up to the third term exactly. So my approximations have started from the fourth term. So this is the central difference second derivative approximation. These are typically very easy to do. And if you recall our option contracts, you will see that most of the cases that we are going to handle will involve only the first and the second derivative. If I recall the Black-Scholes PDE in particular, it requires only up to the second derivative. Second derivative in x, first derivative in t. So for most of the common applications, I will not need more than the second derivative. So this kind of approximation will be sufficient. If I need higher order derivatives or higher order accuracy in particular, then of course I can derive them. I can extend this method and derive more complicated expressions, but it will be cumbersome, so we won't get into that. The important thing is the first two derivatives up to a very good order can be done using the central difference. And good news for you, there is a section here in this book which I am going to ignore, I am going to omit, but you are going to read. It actually reviews a method for automatically generating the higher order derivatives because it will be done recursively, and that's a homework for you.
Sir, ওটা order of h square আসছে,
And
h cube আসছে।
why is it h square?
h to the power 4 আছে আর কি। fourth derivative এর আর কি h to the power 4 আছে কোএফিসিয়েন্টটা, আর h square দিয়ে ডিভাইড হচ্ছে। h square দিয়ে
Oh,
divide
h square, yeah, right. I'm dividing by h square now. Sorry, right. Yeah, absolutely right. It will be h square. This part I completely missed. I have to divide by h square now. Correct. Thank you. Very good. Very good. Okay. Okay, that is right. Because I am dividing by h square. Okay. So fine. So then this is the central difference approximation for the first and second derivative with reasonably good precision, and you need to study the higher order derivatives, how they are generated numerically. That's an homework which I will not talk about. I will move on to the applications. So what I want to really talk about is how these finite difference methods will be used for our PDEs and PIDs. So now we'll start our discussion with the heat equation. If you have done a PDE course, this is the classical heat equation. If you have not, forget it. All you need to know is that if you look at the Black-Scholes differential equation, that can be transformed into a PDE of this type. So if you know how to solve the one-dimensional heat equation, you know how to numerically solve the Black-Scholes PDE. The structure is somewhat similar and it can be made equivalent by some change. So this is a derivative with respect to time, and this is a derivative with respect to the other variable x. So ut minus ku kappa u xx equal to 0 is the classical heat equation. And the range is x is between a and b, so there is a finite interval, and tau, time, is between 0 and capital T. I will need some initial conditions. So at time 0, the process starts from fx, and at the terminal time, the boundary condition is that for the boundary A, this is the function for u, g tau, and for the boundary B, this is the function for u, h tau. So at time 0, the function is fx, and at the upper and the lower barrier, the functions are g and h. So if we have these initial and boundary conditions, we can solve this PDE. So is the situation clear? The object that we are going to study?
Yes, sir.
This is known as the heat equation. You may or may not have seen it before, but this is a very well-known PDE. In fact, this is the first PDE that you would solve if you are taking an elective PDE course. I don't know whether such a course exists anymore, but it used to exist in our time. Does it exist now? Any course on PDE available in MSTAT now?
No, sir.
Oh, no, of course. I thought so, but anyway. So this is the first equation that we learned how to solve. And for us, it is relevant because the Black-Scholes can be mapped to a heat equation. So we really need to understand how to solve the heat equation. For that, we need these initial and the boundary conditions. So boundary conditions are like the ceiling and the floor. The initial condition is at time 0. How does it translate to the numerical analysis world? I have this domain, x between a and b, time between 0 and capital T. I have to first make a finite grid, a discrete grid in place of the rectangle. So that's a rectangle. I convert it to the discrete grid for numerical analysis. So what we do is this capital D is our continuous domain. That is now converted to this capital D bar here, which is defined through these two step equations. So what happens is I construct equally spaced grids where on the x axis, the steps are size delta x. How do I get delta x? I split this interval A to B into capital N many pieces. So this length B minus A is divided by capital N. And similarly, I slice the time axis domain 0 to capital T into capital M many pieces. So this is T minus 0 by capital N. So I have an M cross N discrete grid of equally spaced points. And the points are defined like this. Xj start from A, goes in steps of delta x till it reaches B. Tau k start from 0, increases by steps of delta tau till it reaches capital T. This is an example grid. This is an example grid where the horizontal axis is the time axis and the vertical axis is the x value axis. So typically we are used to saying x-axis here in the horizontal, but now x is on the vertical because time is in the horizontal. So it is t comma x system. And here I have 1, 2, 3, 4, 5 time slices. So my capital M is 5, and 1, 2, 3, 4, 5, again 5 space slices. So capital N is also 5. So it's a 5 by 5 grid. And how are the initial and boundary conditions translated here? They are shown in the bold lines. So bold black lines indicate initial condition on this vertical and boundary conditions on the floor and the ceiling here. It is assumed that these functions are supplied to us. These are non-initial and boundary conditions. So when I start computing, I know the functions f, g, and h. These are supplied to me. I know f, g, and h, and I know this equation. Then this is the starting point for my numerical analysis. So to apply finite difference, I will also need to convert my PDE into its discrete version. So it will be like a difference equation. So u tau is a first derivative that I will approximate, and uxx is a second derivative that I will also approximate. And this is where the choice of approximation techniques come in, because I have alternatives here. I can do a first order approximation, I can do a second order approximation, I can use forward difference, I can use backward difference. The difference equation will look different. Even though the original heat equation is the same, the approximated difference equation will depend on what kind of approximation I am taking on u tau and uxx. So we will actually see what is the effect of these alternative choices. Effect in the sense in terms of the order of error, the order of magnitude for the error. So this is what is written here. So how we do this, how we write this difference equation will determine what type of finite difference techniques we are using. Forward, backward, central, etc. And in the following sections below, we will be performing these different discretizations and solving the corresponding difference equation. So our objective will be to show how different types of discretizations lead to different kind of precision, different level of precision. What will be our notation? Our notation is that small u jk is the true value of the function u at this point x equal to xj and tau equal to tau k. That's the true value. And capital U is the discretized approximation value. So if we are approximating, we use the symbol capital, and if we are using the true value, we are using small. Because U is an unknown function, except at the initial and the boundary condition places, the functions are known only here on the bold lines. So we will be using the capital U mostly. So capital U for inside the box. Okay, is this clear so far? This is the setting of the problem. So if this is clear, then the rest will be very easy to follow.
Yes, sir.
So this is our strategy. This is just the numerical strategy, and what kind of approximations we do, that's the content of the chapter going forward. But the strategy is this. We will make different choices and see how this grid is going to be filled up. So basically numerical analysis is all about filling up this grid. I know these points and I want to fill up the remaining points. How fast I can do it and how precisely I can do it is the subject matter for this chapter. Okay. So the first scheme, as I said, there are explicit, implicit, then two others. So we'll start with the first scheme, explicit discretization. And what does it do? In explicit discretization, we use only the forward difference in time scale. So u tau here will be approximated by a forward difference. So I want to discretize my PDE at any particular grid point xj tau k. So xj tau k belongs to d bar here, typical point in d bar, xj tau k. So for a typical grid point, call it the reference point, we use a forward difference for the first term, u tau or del u del tau at xj tau k. And we use a central difference for the diffusion term. So the second derivative term is actually called the diffusion term for obvious reasons. So that is approximated by a central difference, but the first term, the time derivative, is approximated by a forward difference. So this is our approximation for the time derivative. Forward difference at xj tau k will be jk plus 1 ujk by delta tau, order of h. Central difference for the diffusion, second derivative term. So I have this ratio, order of h square, as we have already discussed. So what is our equation now? So at xj tau k, our approximate heat equation, we call it the approximate heat equation because I am ignoring all these errors of the order delta tau and delta x square. If I ignore them, I have the approximate heat equation as 321. And remember that I'm using capital U because I may not know the exact function values at those points. As U is an unknown function, I will not be knowing them everywhere. So I use the capital U. Because remember that small u are the true values which are known only at the boundaries. But inside, I have to use capital U. So I have this difference times minus kappa, this difference equal to 0. That's my equation. This is of course approximately 0, but we are going to solve setting it 0. And we know that the discretization error here is of the order delta x square and delta tau because of the central difference and the forward difference. So how does it work? So because we are doing a forward difference in time, we always move from left to the right. So if you look at this equation here, you will see that to compute this shaded circle value at time k plus 1 and x value j, I will need these three values. Is this clear? If you look at equation 321, you will see that if I give you the vertical slice at k, then I know all these terms except the first one. And because I have an equation, I can solve for this first term, which is the shaded circle, in terms of these three terms.
Yes, sir.
So forward difference is also geometrically going forward because we write, our writing style is from left to right. So we are going from left to right. But of course,
Sir,
yes,
আমরা সেন্ট্রাল ডিফারেন্সটা কেন ইউজ করছি না?
we will. করবো আমরা।
মানে এটা একটা পার্টিকুলার কেস।
Yes, because there are 4 schemes we are going to discuss. You see, any scheme that you use, obviously they will be differentiated in terms of computational complexity and order of approximation. And we all know there is no free lunch because we are doing finance. So if I want to achieve a better approximation error, then I must pay for more computation. That is typically the case. So we start with some simple schemes with reasonable error of approximation. If I want to improve here, then I must pay a cost here in the calculation. We will see that. So explicit finite difference scheme works like this. So just in words, to solve the PDE at point xj tau k on the entire grid, we simply apply this technique recursively, starting from the left, because at the very left, I had the initial condition. And we move to the right until we get to time t equal to capital T. So what people will do is typically they will solve for all the points in a time slice. So all the points on a vertical will be solved simultaneously by rearranging the corresponding finite difference equations. So I do not solve only for ujk plus 1. I actually solve for all the j's, all the possible j's for fixed k plus 1. So we solve for all the points in a time slice simultaneously by rearranging the finite difference equations using the previous values, the previous time slice. So if I try to write it as a system, I will rearrange 321 so that ujk plus 1 can be written simply like this. So ujk plus 1 minus ujk from here, I multiply things by delta tau so that this side becomes free. This constant k delta tau by delta x square, which we will call rho. We will call this rho times the central difference part equal to 0. It's just rewriting 321. Why? Because I want to write ujk plus 1 as an explicit solution target. So ujk plus 1 is rho ujk minus etc. For, and here I have done some simplification because ujk appears on both sides. So ujk has a different coefficient. The other two has rho. This has 1 minus 2 rho. This will work for all j's from 2 to capital N and for all k from 1 to capital M. Remember, for j equal to 1 and j equal to the last one, I already know the function from the boundary conditions. Boundary conditions are known functions, as we have already assumed. So I need to solve for the inside of the box. So ux1 tau k is g tau k, uxn plus 1 tau k is h tau k. And of course, if I put k equal to 1, then uxj tau 1 is also fxj, which we call fj. Because again, I am evaluating at discrete points. So it is just fj. These are already known. So all these grid points, top, bottom, and the left, it is already known. So the approximate PDE, this 322 approximate PDE solution for this time slice can be written in vector form like this. So this is where our linear algebra comes in very handy, because now if you see this structure is very much amenable to vector matrix kind of notation. So this is our time slice. Tau k is k minus 1 delta tau. Uk is the vector of all the time k values which are inside the box. So for j from 2 to capital N, they are stacked here for a fixed time slice k. So a fixed vertical, a complete vertical is uk. Then I write 322 together. 322, all the equations of 322, all the equations mean for the whole, for all the j values on a time slice, I write all of them together as a matrix equation in this one. So uk plus 1, which is same thing as uk for k plus 1, is equal to a explicit times uk plus rho times this vector, where I have the two I have the two boundary values which are known, and the rest inside are all zeros. This is adjusting for the top and the bottom, because the top and the bottom are already known to me. And A explicit, that is easy to understand because I have this row 1 minus 2 row and row structure. So all the rows inside will be of this form. Only the first row and the last row will be missing the first term and the third term. So these will be for the top line boundary condition and the bottom line boundary condition. Because for j equal to 1 and n plus 1, things are already known to me. These are already known to me, g and h. Okay, so is this scheme clear? So I'm just stacking all these equations together, writing it in a matrix form so that I can write the algorithm in a very compact way.
Yes, sir.
Sir, A matrix and UK vector is of dimension n plus 1, right?
N plus 1.
Yes. So yes. So actually, the UK vector
UK vector
above is given as n minus 1 dimension. So they may modify it a bit.
modify it. Yes. That sits up for you. Good. So, but you see, remember, do any of you know the, well, that's a long story. We'll talk about it some other time. So basically, it's a check that whether you are paying attention to the class. So this is the algorithm for the explicit scheme. So I define U1. U1 is for the first time slice, which is initial condition known. F values known. For k equal to 1 to m, I have this system of equation, which I will solve recursively because the output from the earlier step is input in the next step. The final solution at time capital T, which is tau m plus 1, will be um plus 1 like this. Again, I have to add the last and the first and the last term here correctly. So this is the total algorithm for the explicit scheme. The explicit scheme has this tri-diagonal matrix. So this is important because you see the solution here requires matrix multiplications. Each step I am doing a multiplication of a matrix with a vector. So that means I am doing some known number of operations, multiplication and addition operations. Because it's a tri-diagonal matrix, I know that here the order of operation will not be n squared, but of order n. Because in each row, I am only doing at most 3 operations. By the way, is it making sense? This order of computation kind of considerations, have you ever come across these things?
Yes, sir. In algorithms, we did.
Yeah, because in algorithms, if we talk about, see, if I want to invert a matrix, what is the order of computation? If I do multiplication, addition, things like that, right? So because
Yes,
it's a tri-diagonal, I know that I am doing exactly 3 operations per row. So it is not like n squared, but 3n. So it's an order of n. So this is the computational complexity I am facing when I am using the explicit scheme. That's my cost, because at each step I have to do it. So it becomes n into m order of operations. But benefit is this. I know that the precision I am getting is square in the space axis, vertical, and linear in the time axis. So order of delta tau and order of delta x square. So that's the precision I am getting with these many operations. So we will discuss this later when we compare the different schemes in terms of their precision and cost. But this is how these things are determined. Just counting, simple counting, nothing else. And you have an algorithm which is pretty simple. So it's a very small code, very quick code, which you can write and run, and you know what will happen. All right. So that's enough for today. We will continue this discussion next week, but job for you, chapter 1 and chapter 2, you have to now study the chapter, start doing the problems. If there are issues, we will discuss. Chapter 3, I have already given you one homework, which is studying section 3.4, because I'm not going to discuss the higher order derivatives, but I'm going to ask you such questions in the exam if I want. And next week, we are going to continue with the other three finite difference approximation techniques. Any questions at this point? Otherwise, we will stop for today. I think this is a good place to stop.